Hello, I'm Dan Ridley-Ellis from Edinburgh, Napier University. It's the morning of the In Future Wood webinar. I'm just checking my slides and I figure I might as well do a long version of the presentation that I'm about to give because we've only got half an hour to cover the whole topic of grading of secondary timber and inspection of timber in buildings, and that's not nearly long enough to introduce the topic and have a good discussion. So here is a presentation of unknown length. Well, you know how long it is because you can see it on YouTube. At the moment, I don't know how long it's going to be. I'm just going to talk on the topic and try and pick out some of the key things. Even then, it's not going to be a complete look at this whole thing, but hopefully it will answer some more of the questions that we don't have time for in the webinar. So this is a presentation about Work Package 5, which is about sorting, assessment and grading of timber in existing buildings. Some introductions. Edinburgh Napier University, that's where I'm from, and we're leading this work package. I personally have been working in the area of wood properties and grading for a number of years, about 15-16 years, and I'm quite active in the whole standards development side as well, so I sit on the committees that write the standards to do with structural grading. But actually most of the work in Work Package 5 is being done by colleagues at the Technical University of Madrid and University of Ljubljana. So Spain and Slovenia, they have more time in the project than we do, and probably more expertise in some other things as well. And my colleagues might not agree with everything that I'm about to say. This presentation here is going to be really my thoughts rather than necessarily agreed opinion within the project. National University of Ireland Galway is also involved in this, primarily because they're also doing the work package to do with new products from recovered wood, for which you need to know the properties. And the other research partners are all connected with Work Package 5 in one way or another through their own work packages. So a quick summary as to why we need to have this work package. Why are we interested in strength grading of secondary wood? So if we are going to use recovered timber again, then we need to have some properties to use in timber design to ensure that we have safe use of this recovered wood. And we ensure structural safety for new wood by this process called strength grading, or stress grading in the old terminology. The problem is that the current rules and standards for strength grading cannot possibly work for recovered timber because of a number of unknowns, which are either very difficult to know for recovered wood or impossible. So those include knowing the species, knowing the growth area, knowing the previous grading that might have happened to the wood, and that's the really difficult one. And also, what were the original properties of that original population? If it's old timber, then likely the properties of the wood that were coming from the forests in those days are not quite the same as they are for modern wood. And we also don't actually know what happens to wood over time in service, because things can happen to it in service and things can happen to it as well when the building is demolished. And we don't know, at the moment we don't have enough information about what's happening to the wood to be able to grade it safely. So that's why we have Work Package 5. But there are some related issues as well. First one is that it's currently very expensive to establish new grading rules for a new species or new source, or even a new grading machine. And this acts as a barrier to get a wider range of different species into the industry. Reason for this is that we require very large testing programs to establish the grading rules. And if it's a minor species or a small source, sometimes that testing program can be a significant proportion of the wood that we want to use, and obviously that's not an economic thing to be able to do. So at the moment the grading rules that we have are acting as a barrier to get new, more diverse range of first use timber into construction too. There's also no current easy way of assessing timber in situ. to give values for structural calculations. Now, obviously this happens because we have to do it, but the problem is that it's a bit more of a seat of the pants process than it ought to be. There's no real kind of good framework for it. Because of that, we have to be careful what we're doing, and perhaps sometimes be a bit over-conservative, which sometimes means that we either can't keep the timber in service, when in reality it would probably be fine, or we have to put in some extra strengthening that might not be needed. So it would be good to improve this whole issue around retaining timber in buildings, because if we have that option, it's probably the best thing to be able to do for the circular economy, is extend the lifespan of the timber that's already being used. And actually we don't have any proper ways at the moment of strength grading modified wood, like thermally modified wood or chemically modified wood, or even, surprisingly enough, good ways or standard ways of grading anything that's not rectangular cross-section, including round wood. These are missing actually from the current standards process, which is a bit of a hole. So there is on-demand webinar content, and if you're watching this video, then I guess you know about that. And I recorded earlier a video presentation about the other ways in which strength grading can get in the way of the circular economy, including things like increased focus on a smaller number of species and ever decreasing number of strength classes on the market. I talked a bit about how when you go to these commodity strength classes, you actually discard some of the potential of the wood, and sometimes you're not putting things on the open market and it doesn't actually make sense to discard the timber potential. And how sometimes the whole process of grading makes us think incorrectly about it, and that leads sometimes to over-specification, which is another circular economy issue, in that we're using or specifying wood that is actually way better sometimes than it actually needs to be. So watch that video if you're interested in those topics. My other colleague at Edinburgh, Napier University, Marlin Kramer, has made a couple of videos on other aspects of grading recovered wood, which are touching on things like the more practical issues, and the things like the equivalent of visual override that you would need, and the things that you find in recovered wood that you don't find in new wood, like holes, fasteners, notches, non-rectangular cross-section, mechanical breakages, things like that. And I also did a video looking, a very short video looking at different grading machine technologies as well, with a view to how good or bad they would be for grading secondary timber. Now, in an ideal world, we'd be able to use any kind of grading technology because we don't want to limit the market in any way, but there are some machines that have certain advantages and disadvantages. Now, as we're probably going to talk about, one of the issues is that the current machines, they're using a system that was developed for the time when machines were quite stupid, and all they could do was just look at a single piece of timber and apply a simple rule like pass or fail. And they couldn't remember what they'd done previously. So it was just look at a bit of wood, does it pass or fail some criteria, and then mark it accordingly. With modern machines with computers attached, they can actually look at what they've just graded, and potentially they can change the thresholds or the decision criteria in order to adapt to changes in the timber quality as it comes in. The standards have recently opened up with something called adaptive settings, which is a little bit in that area, but there's a lot more potential that we can do with modern grading machines and modern computer technology. So I guess the summary here is that possibly many different kinds of grading machine would be appropriate for grading recovered wood, but the key thing is to be able to link it to a computer, and for that computer to be able to change on the fly the thresholds for the grading. So this is the current situation that we have with timber grading. We have new timber coming in from the main commercial species and commercial timber producing forests, and that is strength graded, usually by the primary producer, the sawmiller, and then it gets used in the manufacturing of construction products. And by manufacturing of construction products, I mean timber frame kits, but also construction on site too. So that gets used in buildings and bridges. That's what the strength grading is for. And then it gets used. We have some way of kind of inspecting it again if we're doing renovation and repair and retrofit and change of use of structures, but I put a dotted line there because it's not easy. And then when buildings and bridges get demolished, the wood is collected at the moment, but it's mostly going to either panel products or energy, because there is no linkage back from the recovered wood to manufacturing of new construction products. So at the moment this bit is missing. This process of grading again the wood or assessing again the wood is missing. And as I said, this process here of inspection, it happens, but presently it's not easy. So this is the situation that we would like to get to, is to get that linkage in, so that we can take recovered wood from deconstruction and we can assess the properties well enough that we can manufacture new products from it, new construction products, and use them safely. So that's the thing that we want to improve with this work package and this project, is to improve the segregation of grading of secondary wood to get it back into new products that are a higher level than the panel products that are currently going, so that we can extend the service life of the wood, increase the number of cascades in the material cycle. And we also want to improve this grading process for minor species and other alternative sources as well. It's kind of a linked problem, and if we can solve this issue down here, then we can probably solve this one too, hopefully. And part of the project is to improve this in situ assessment of wood already in service, so that we can improve it and retain more wood in its first use for longer. So if you're interested in the topic of in situ inspection, I would encourage you to watch this other on-demand video by my research colleague in Madrid, Guillermo, and he covers the topic of inspection, estimation of properties, calculation of load carrying capacity, and presents a case study. So if you're interested in that topic, I'm not going to talk about it much in this video, so you're probably better off watching that one. Okay, so a little bit about grades and strength classes and design values. They're not quite the same thing as each other, so let's unpick this issue. So when we grade timber, we sort it into grades, and grades are really just sets of pieces. So we can sort timber into a pile that says this is a good pile, and another pile that says this is a bad pile. And those two piles are called grades. They're just sets of timber. There's nothing else attached to them other than that they're just piles of timber. Grades are linked to strength classes, so you need to get to a strength class in order actually to have some design values to use in your calculations. So strength class is a special case of a grade. It's a grade with some numbers attached, some description of the properties of the wood collectively in that pile. Now, strength classes, they're a convenient way of listing the design properties, but that's a convenient way. It's not the only way. You could just list the design properties, because that's, at the end of the day, what you need is the design properties. It's not the strength class. But if you're putting stuff on the open market, the normal way of selling wood, then strength classes are the easiest way to do that, because you just say this is C24, this is C16, this is D18, and everyone knows what that means when it comes to the design properties. So they're a shorthand way of talking about performance, but grading isn't about strength classes. Strength classes are just a convenient way of talking about design properties. And design properties, they're always about sets of pieces rather than individual pieces. Hopefully that will become clearer in a moment. So structural design is based on probabilistic description of material properties, because we never have perfect knowledge of material properties. Whatever the construction material that we're dealing with, we don't have perfect knowledge. So we have descriptions of uncertainty. This is how design codes work, how structural engineers deal with uncertainty in materials, is that they have this probabilistic description. But probability distributions are difficult to do calculations on, so we still need to boil it down to single numbers. And the two kinds of number that we boil it down to are the means and the fifth percentiles, and we call these characteristic values. So we use the mean value as the characteristic for stiffness properties, and we use the fifth percentile, the lower fifth percentile, as characteristic descriptions of both strength and density. Now density here, we're concerned about low density being an issue. So density is a proxy for things like fire performance and connection performance. So we're worried that the density is not high enough. This is not density for self-weight. So that's why it's the lower fifth percentile. So the mean, you all know what that means. Fifth percentile is basically saying that 5% of the pieces are below this and 95% of the pieces are higher than this. Now, we don't know any individual piece, we don't know whether it's below the limit or above the limit. We just know that, statistically speaking, there's a 5% chance that it's below and a 95% chance that it's above. And you might think, well, why don't we just use the minimum value? Well, the truth is we don't know what the minimum value is, so this is kind of like a way of describing the minimum. And the fifth percentile, we use that because we stand a chance of being able to estimate what the fifth percentile is. And that's all handled within the design codes, how they deal with this calculation and allow for the fact that 5% of the pieces are below the characteristic values, all handled in the design code. So if you're designing timber, you would be familiar with the list of design properties in EN 338, the European standard that lists the properties for the C, D and lately tension classes. There are other strength classes too that don't appear in EN 338. But the main ones are the C classes and the D classes that would be used in construction. That's where you find the properties. And there are three primary properties, the ones that are highlighted in the standard: bending strength for C and D, the mean stiffness in bending, and the density value, the fifth percentile density. So those are three primary properties. All of the other properties are called secondary properties, and they are usually estimated conservatively from equations based on the primary properties. And you find those equations in EN 384. So if you look in EN 384, you find a whole bunch of equations that say, given certain strength, certain density, and certain stiffness, these are what all the other secondary properties are. That's not quite all of the secondary properties, so you will find in Eurocode 5 a few other cases, a few other properties that are calculated. For example, from density, you would get embedment strength. So there are some other design properties that you estimate from the primary properties. So yeah, you've got certain strength classes, and you would just look up what strength class you've got. These are the design values that you can plug into your calculations. Pretty easy to use. That's the whole idea of strength classes, is that they're easy to use and you don't need to know where your timber is coming from or what species it is. You can just say, I did this design for this strength class. As long as the timber is this strength class, the design is fine. I don't care where you get it from. So that's the whole point of strength classes for new timber. So why do we have this problem with the current grading standards? Why are they not suitable for recovered wood? Well, the reason is that the grading standards, well, they have to work with the old technology. So everything has to be backward compatible for new timber, because these old machines, they're still in use in the sawmills. So visual grading rules, the rules have to be simple. For visual grading, you're just sorting timber into grades according to specified criteria. You can't adjust those criteria, it's just sorting and applying the rules. For machine grading, the criteria for sorting are easier to change, but the grading still works on as I say, a one piece at a time decision-making process, even though the grading itself is about populations. So we have to assume that the machine can't remember what it's previously graded, and it just applies, like a dumb box, it just applies a rule to the timber. And the other thing is that, well, this whole system was made for new timber, and actually for timber on the open market when the end use of the timber is not known at the time that the grading is done. And every bit of the standard is written for this whole purpose, and it's really about ease of trade primarily. So that's why we have these commodity strength classes, to make trade easy. Now, I talk a bit more about when it makes sense to use commodity strength classes and when it doesn't in this other document that you can find on the on-demand webpage, a conference paper from 2016 that gets into that topic a bit more. Okay, so let's look at a very simplified example. If you know about grading, then you will immediately see how overly simplified this is, and some of the things that aren't quite right. If you don't know about grading, it's already going to be complicated enough. So I'm not really going to get into the ins and outs of how this differs from real grading calculations. So let's just say this is a very simplified example and just take it from there. So this is real test data that we're looking at for UK ground larch, almost 650 full structural sized specimen. So that's timber with knots, grain deviation, like typical timber that you would get, sawn timber that you would want to use in construction. We've got three graphs here. The first one is plotting whole board density against bending stiffness. The second one is plotting whole board density against bending strength, and the third one is plotting whole board density against density sample density. Now, I'm going to use whole board density as the grading criteria, the indicating property, the IP, because everyone thinks that density is a really good indicator of timber quality, and it isn't. So I want to illustrate that. In real grading situations, you very rarely use simple density as your grading parameter because it doesn't work very well. There are usually better ways of doing it. But I'm going to use whole board density just to show you how well or not well it works for new timber. So this is real test data where we've tested the timber. We have actually broken it, so we know the real strength of that wood. Of course, once we've broken it, we can't use it. So we have knowledge here that we wouldn't have in a real grading situation because we can't afford to break the wood. We still need to have the wood to use it. So let's look at the first graph, which is whole board density versus bending stiffness. There is a reasonable correlation to be seen here, R squared of almost 0.4. So yeah, the denser pieces, they do tend to be a bit stiffer. Second graph, whole board density versus bending strength. You see almost no correlation here. The R squared is very low. And actually this is quite typical. There's nothing special about larch or UK ground larch here. The correlation for within a species, the correlation between density and strength, mechanical strength, is pretty low. You can look in this report from the Gradewood projects, very big study that was done with testing timber across a number of different countries in Europe. And it's a really good report full of very basic data that you can have a look at. I just pulled up a couple of tables, and the data in the circle here is showing the correlation between whole board density and bending strength for spruce and pine, grown in several different European countries. So the first one, spruce, there were 2,776 specimens tested, so there's a big testing program, and the correlation between the whole board density and the bending strength is down at 0.25, so quite similar to what we saw with UK grown larch. Smaller data set for bending in pine. It was only 430 specimens, but you can see again the correlation between the density, whole board density, and the bending strength is pretty low, down at the 0.2 level. So nothing weird about UK grown larch here. The fact that there's very little correlation between whole board density and bending strength is expected, actually. Third one, you might be wondering, like, why isn't there a perfect correlation between density and density when there should be? The thing to realise here is that for strength classes, for assigning grade, the density is the density of a small sample of clear wood taken from the board, which will differ from the average density of the density of the whole board. So there is a slight difference between those two things, which is why we don't see a perfect correlation here. So one is whole board density, the thing that we're using for the grading decision in this simplified example, and the density that we use to decide on design values, which is the density sample, the clear wood density. But it is a strong correlation, R squared of 0.84, so the correlation between the density sample density and the whole board density is pretty good. So if we don't do any grading at all on this timber, we could just calculate what our characteristic values are. So what strength class would this correspond to? Well, the mean stiffness is 9.69 kilonewtons per millimeter squared. I seem to have forgotten to put any units on this slide, which is very bad. Stiffness 9.69, which would be enough for C20. The 5th percentile strength is 21.8, which would be enough for C20, and the 5th percentile density is 408, which would be enough for C40. So actually, the timber is dense. Larch is a dense species, but just because something is dense doesn't mean that it is also stiff and strong. So if you didn't know anything else and you just had some larch and you measured the density and you found, well, the density looks like it's good enough for C40, you might be tempted to use the strength and stiffness values for C40. But it doesn't work like that. The strength and the stiffness values for larch are actually much lower. So if we were assigning this to a commodity strength class, we would have to use C20, because the strength and the stiffness both limit the assignment to the strength class. They are both only appropriate for C20. They don't meet the requirements for C22 or anything higher. So we have to say that it's C20. And you can see when we do that, we throw away a lot of the potential of the density, because we'd have to use in our design calculations the density for C20. We'd have to use the design values for density of C20 as well, even though the real density is higher, and we could safely use the density values of C40, which might help, because many structural designs, the member sizes are governed by the connections, which is a density thing rather than a strength and stiffness thing usually. So yeah, if we don't do any grading, we would be getting C20, which is not far off what the real grading calculations come out for ungraded UK grown larch. It does come out to about C20 if you don't do any grading to it. But let's do some grading here. Let's say that we will only accept boards that are denser than 460 kilograms per cubic meter, and we'll reject every board that is less dense than that. So this is a grading threshold. 460 kilograms per meter cube. Now if we do that, we get rid of some of the lower stiffness pieces because there is that good correlation, or reasonable correlation between density and stiffness. We get rid of, well, we get rid of some of the weak boards, but because there is no correlation hardly between board density and bending strength, we don't do a lot to the strength. And then for density we do, because we can almost directly grade for density, we do get rid of a lot of the low density pieces. So let's look at how that's improved the characteristic properties. Well, we've raised the mean stiffness by doing this. We've raised it to 10 kilonewtons per millimeter squared, which is enough for C22. The 5th percentile strength we've raised to 22, which is also good enough for C22. The density, we've raised it, and now it's good enough for C50. But if we are assigning this to a commodity strength class, then we have to use C22, even though the density is higher, because it's, again, limited by the strength and the stiffness. So by doing this grading process, by getting rid of the least dense boards, we have improved the design values for our timber from C20 to C22. Now, if we had different means and different standard deviations and different correlations for our timber, then the calculations would be different. So we can't take another source of timber or another species, apply the same density threshold and expect the same results, because the correlations are different, and hopefully you can see our characteristic values, they're based on everything that's passing, so they're descriptions of everything above the threshold rather than individual pieces. So you'll get a different result depending on how much of the population ends up over the threshold. So that's a very simplified example of how we would grade new wood. What would happen if some other process had taken away the densest boards? What would happen if we didn't actually have any boards denser than 550 kilograms per meter cube? They were missing from our data set. Something had happened. They'd been graded out, or they'd been sorted. Some process had removed them. Now, we would lose actually some of the very stiffest pieces in our data set. They would have disappeared. We would also lose some of the strong pieces, but again, because the correlation between board density and bending strength is not high, not a lot has happened to the strength. And we would lose the very densest pieces as well. So if we didn't know about this and we applied the same grading threshold as we did before, we wouldn't actually be achieving the properties that we thought we were. So the mean stiffness would be, instead of 10, it would be down at 9.42 kilonewtons per millimeter squared, which is not suitable for C22, it's only suitable for C18, so it's actually worse than it would be for a complete ungraded population. The strength is also reduced a little bit, not by much because of this poor correlation between density and strength, so that's reduced, and it's now down at the C20 level. So we thought it would be C22, but in reality it's only C20. And the density, not much has changed to the density, even though we have lost those very high density boards. The 5th percentile hasn't changed very much because we can grade very sharply for board density. So even though we're missing that top end, the 5th percentile is more or less unchanged. So we thought it would be C22, but actually it's only really got the properties of C18. So hopefully this illustrates why the grading rules don't work if there has been some prior grading process or some process that has modified the population. The grading rule is based on knowing what the ungraded or before grading population is like. And if anything has changed about that population, then the grading rule, we can't rely on the grading rule to work as we expected. This is a very simplified example looking at grading of timber there. Now, key thing to remember about the properties or the things that we use for making our grading decisions. There's a whole list of things that we can use, like ring width and knot size, stiffness, like a whole bunch of things that we can use as grading indicators. And they are correlated with the properties that matter. So when we're talking about structural grading, it's not knots per se that matter, it's the strength and the stiffness and density that matter. So knots are, we know they affect strength. So there is a correlation there between knots and strength, and that's why we can use knots as a grading parameter. So there's the correlation between, for example, knots and strength. But there are other correlations there. So actually, strength, stiffness, density, they're probably more determined by how the trees grew and how they were processed. So the forest management and the climate and the situation, the local situation, because the trees are growing wood for their own purposes, and they'll grow wood with properties that suit their needs at that particular time. So actually it's the growth conditions and some aspects of processing that actually determine most of the mechanical properties. And they also determine the grading characteristics. So there's a correlation between knots and growth conditions, for example, and there is a correlation between growth conditions and strength, which means that we see a correlation between knots and strength that might actually be mostly coming from the fact that both of those things are influenced by the growth conditions. It's not that knots are totally determining the strength, it's the growth conditions that determine the strength, and they also determine the knots. So there is some things like they're correlated, but it's not a causal correlation for all of the things that we use for indicating properties, and that's why grading rules don't necessarily translate from one growth area to another, because the growth conditions might be different, and there might be a different correlation between knots and strength, for example, because the trees are growing further apart, or they're a different age, or something has changed about the knots, and that changes the correlation between knots and the mechanical properties. So that's why we can't port across a grading rule easily from one species to another, or one grading area to another. That's why all the grading rules, we have to know the species and we have to know the origin, because of this issue here. So just because something is used in grading, especially in visual grading, doesn't mean that it's directly linked. It's like, it doesn't mean that knots determine strength, it means that knots are an indicator of strength. It's not a it's not an entirely deterministic relationship. So this, in reality, it's not as strong as people think, this link between the grading indicator and the actual property that we're trying to grade. And if anything changes in this original population, if we change the growth conditions, if we change the seed source for our trees, or the climate changes, then that potentially can also change the way that the grading has to work. So that's why there might be different relationships for old wood compared to modern wood, because the growth conditions were different in the past from how they are now. So we can't do a testing program of new timber and necessarily expect the same result for old timber. And this is especially true for knots, ring width and density. So those properties which are key to grading, or many types of grading, because we use them so much, we think they do determine the strength and the stiffness, but in reality a lot of that is determined by the growth conditions and not necessarily per se by the size of the knots and the rings themselves. It's just that both of those things are correlated with growth conditions, and that makes them possible to use in grading, but also means that those relationships don't transfer from one species or one growth area to another. Now, we might have a simple solution here because we do have grade stamps on timber often. So, yeah, could you, if you had some timber and it came from a building, could you just look at the grade stamp? Is that okay? Well, maybe, but there are a few things that we need to consider. Firstly, well, maybe it won't be readable. You've probably all been to a timber stockist and struggled to read some of the brand new grading stamps, never mind ones that have been in buildings for years and got covered up in dirt and other things. So you can't necessarily rely on the grading stamp because you might not be able to read it. And probably, if the timber is old enough, that grading stamp will relate to old standards, and it might not be an easy way, like it might not be easy to transfer that old grade stamp, what it meant, into a new design code. So the grade stamp might relate to, for example, a permissible stress design, and you might want to use a Eurocode 5 limit states approach. It means that you then have to somehow translate the design values from one code philosophy into another, which is not necessarily easy to do. And also, we can't necessarily rely on the fact that standards might have changed. I mean, standards do change. Even the design values in EN 338, especially the ones for the secondary properties, they do change when the standard is updated because more testing is done and we discover things, and we think, oh, we have to change the numbers in the design to make sure that it's always safe. So that's quite a long-winded way of saying that yes, possibly you could use grade stamps, but might not be that easy, and they might not be that reliable. And also, well, the properties might have been degraded, so it might have been that grade when it went into the building, but over time things have happened to that wood. There's been changes in humidity and moisture, and the thing's been loaded. Maybe the properties have reduced somehow, which means that it no longer has the properties that the grade stamp said it had. And actually, maybe you don't have a completely random set of boards. Maybe some process, deliberate or accidental, has somehow sorted that population, and you don't anymore, even though you have a set of boards with a stamp on, maybe some process has taken away the worst boards or the best boards. So you don't necessarily know that you still have something that represents the stamps that you see on the timber. And the whole question of legality. So if you were reading the grade stamp, well, who is legally responsible for that performance? Is it the person who originally put that grade stamp on the wood? Well, probably not, because you don't have all the paper trail. Like, you have the grade stamp, but you don't have the rest of it. So who is responsible? Are you confident enough that you could take that grade stamp at face value and say, yes, I guarantee those mechanical properties for that timber in the new situation? So yeah, grade stamp is some guide, but it's not a easy answer, unfortunately. But it's not all bad news. So we can do a lot. First thing is that we can think differently about how we're doing the grading. So at the moment, grading is not currently working on predicted values of individual boards. As I say, it's making decisions on an individual board basis, but it's trying to predict the properties of a set of timber. But actually we do have the capability of getting useful estimations of the properties of individual boards, especially for stiffness and density, because those are two things that we can almost measure directly with non-destructive testing techniques. Like density, we can weigh it or use an X-ray densitometer and actually measure the density. We would have a very good idea of what the density of the board is. Similarly with stiffness, we can use a bending elastic load bending test or a bending machine and actually get an estimate of the real stiffness, or probably even better, use a acoustic grading machine to measure the stiffness. So yeah, we could have a pretty good idea of the stiffness of every individual board too. And we could use those estimated properties of individual boards to calculate some design values. I mean, we could do this. It would be hard for strength, but for stiffness and density we could probably do it pretty well. Okay, I'm going to try and explain this. It's a topic that I've been thinking about for a number of years, but probably don't have a good way of explaining it yet. But let's go back to an example of board density, whole board density versus bending stiffness. If we have a particular density board, like we've measured a board and it's 500 kilograms per cubic meter, we know from having done that previous study that there's a linear relationship there, and we can use that linear model to estimate what is the bending stiffness. Like we've measured the density, we can get an estimate of the bending stiffness. And we can use like the standard error to calculate a probability distribution, a prediction interval for that board. We can say, well, there's a X% chance that this board has a stiffness of this. And we can do that for every single board that we measure. So every single indicating property that we measure, we can make a probability distribution for the property. And then we can add together those individual probability distributions and get a combined probability distribution for that particular set of timber, with those indicating property values. So we can add together those distributions, and from that combined distribution we can calculate some design values. We can get an estimate of the 5th percentile density and strength and the mean stiffness. Like statistically we can do this. We probably need a bunch of extra adjustments to allow for the certainty that we need in engineering design, but in principle this should be possible. We can measure bits of wood and we can get estimates of properties and we can get some design values. And for this previous example that I showed, where we were grading for boards above 460 kilogram per meter cube, but we were actually missing everything that was denser than 550. So we can apply that approach. We can look at the individual density values of everything that we saw, and we can add together those individual probability distributions and calculate a population distribution. That's what we're looking at here. So the blue bars is a histogram of the actual test data, and the red curve is an estimate based just on the individual IP values and what we knew about the linear regression, this linear relationship between density and bending stiffness, the slope and intercept and the standard error. And it's not bad, actually. I mean, it works. It's certainly better than it was when we were just using this simple grading approach and we had assumed that we have everything in the population above 450 and we didn't know we were missing that 550. So this individual board basis process would work better in that situation. So it's not bad. I mean, of course, in the real world there's a lot more to it than this, but in this simple example, that seems to work reasonably well. But what would happen if, unbeknown to us, something had also removed all of the strongest boards? So all of the boards that had a bending strength above 50 newtons per millimeter squared were somehow missing. They'd gone missing. They weren't there. So when we were grading, we were taking all the boards with a density above 450, but we were missing the ones that were strong, and we were missing also the ones that were denser than 550. So remember back, we thought we would get C22, but because we're missing the densest boards and the strongest boards, the stiffness is reduced even further from 10 down to 9.06 kilonewtons per millimetre squared. So we thought we were getting C22, but the mean stiffness is only good enough for C18. And we've also knocked down the strength. Although we haven't had, like, just because we're missing the strongest boards, like, the strength has gone down, but not much further than it had already gone down from not having those dense boards. And nothing much has changed from the density because of this poor correlation between density and strength. So we thought we were getting C22, but actually we've only got C18, which in this example, not much different actually from the previous one. Losing those strong boards hasn't actually changed that much the design values, but it could have done. It just didn't in this particular example. But let's now try our individual board grading approach. Does it still work? Because now we're missing the strong pieces, and we kind of assumed that they were still there. So now when we have a particular density, we had assumed that we would have also the strongest pieces, but they're missing. So that has actually brought down the blue histogram here. The actual test data has moved to the left because we're missing those strongest boards, but we're still assuming that they're there. So our model, our estimate from individual IP values, is now not as good because we're missing some of what should be over here. So if we're going to use this individual board basis of grading, then we need a way of detecting if there's something missing and adjusting for the fact that it's missing. So we need a better idea than the one that I've outlined here, but it's a stepping stone to how we might approach this. There are a bunch of other open research questions. First thing, like, well, what do we do if the cross section isn't rectangular? How do we grade it? Like, this would include just not notches and things like that, but what if it's got excessive wane or a groove cut in the length? Like, how do we grade it, and how do we come up with some design values? And what if our equations for secondary properties no longer work well because of processes that happen as timber ages and degrades in service? Like, we know that cracks can open up, mechanical cracks longitudinally, and maybe the tension strength or maybe the tension strength decreases perpendicular to grain, and maybe it becomes more brittle, who knows? And maybe then the secondary properties that work fine enough for new timber aren't good enough for secondary timber. So we need to have this better idea about secondary properties, and maybe we need different equations for recovered wood. And what about moisture content relationships as well? As wood ages, just as it's reacting with the air, it loses some of the hydroxyl groups on the wood polymers, so the equilibrium moisture content decreases as timber ages, which means that in any particular humidity and temperature environment, the moisture content would be lower for old wood than it would be for new wood. We would expect this. So then what do we do about our, because we were normally talking about mechanical properties at a standard moisture content of 12%. How do we adjust for our properties to a different reference moisture content when the equilibrium moisture content is changed. We need some way of doing that, and probably maybe some new relationships, or at least to check that the relationships that we use for modern wood to adjust our properties for moisture content also apply for old timber, and we would need a new reference equation. So the standards, it's not the moisture content that's the reference. The reference is actually the temperature and humidity, but if you look in EN 384, you can see that even though the reference conditions are actually temperature and humidity, value of 12 is used in the adjustment equations, because there's an assumption that 12 is the equilibrium moisture content. So maybe we would need to reframe the equations there. And the other thing is, well, if we're going to make something that's equivalent and works as well as the current system for new timber, well, how well does the current system work? This is not something that we completely know now either. There's been a lot of research on that topic, but we still don't know exactly how well it performs. So if we're going to make something that works as well as the system for new timber, we probably have to have an idea about what that actually means. So what do we hope to achieve in Work Package 5? Well, we hope to achieve an approach that's equivalent to the new system, for the current system for new timber in terms of structural safety. And that can also work without knowing the things that you don't know or are difficult to know for new timber, which is the species, the origin, and particularly the prior grading that's happened. So we want a system that we can apply, that's possible to apply on new timber, and that is basically as trustworthy for design as the current system for new timber. Not to replace the current system for new timber, but something parallel to it that's equivalent and compatible with the design codes. And we also need to list some quality criteria that are appropriate for recovered wood, that are addition to the things that you find in the visual override section for new wood. So, as I say, there are things that you find in recovered wood that you don't find in new wood, like holes and fasteners and mechanical breakages and notches. We would need some kind of additional visual override for new wood. So as part of the work package, we're formulating some extra visual override and usefulness criteria, in addition to just thinking about the mechanical performance. And we're hoping to propose some revisions to standards to make them more suitable for the circular economy. Now, revision of standards is a very long process, so that's not going to happen anytime soon. That's going to take years or decades. But there are some things that we can hopefully start to use in the shorter term. So if you're grading timber for a one-off building, or you're grading timber as part of a manufacturing process to produce a one-off product, then you don't have to obey all of the requirements of the construction products regulation. There is an exemption written into the CPR about these one-off situations, which means that you have a bit more flexibility in how you apply the harmonized standards, which means that if we have a process that's trustworthy and been shown to work, it might be possible to actually employ that in the factory production control process, even though it's not fully compatible with the harmonized standard and wouldn't be appropriate if you're just grading timber for the open market. And hopefully also we will develop and demonstrate some methods of in situ assessment or some guidance to allow timber to serve longer in existing structures, because probably if we have that option, that is the best thing for the circular economy, is to extend that first use life as well. But this is it's not the main focus of Work Package 5, but it's part of it because we know that it's important and we know that people are asking for this. So how are we doing this? How are we going to solve these seemingly intractable problems within the lifespan of the project? Well, It's a combination of modelling studies based on very large data sets. So the research partners here have been active in timber grading for ages, so we have large data sets available, and we can use simulations based on those grading data sets to simulate different situations for recovered timber. Like, we don't have enough money or enough time to do large testing programs for recovered timber, so we're going to model what we would get. So we're going to apply virtual grading and degradation processes we apply to new timber to see what happens, so that we can make a new system that's robust enough to be able to cope with those things. So we can simulate based on data that we've already got. But we also need to do some testing and grading exercises on recovered wood, because it's not enough to do the simulations. We need to have some real world situations, some real grading of recovered timber, actually to learn about all of the difficulties. It's not enough to guess and just model. We have to do it in practice and learn from doing it and learn from our mistakes. So part of the project is taking some recovered timber and doing some testing and doing some grading processes. It will not be enough on its own to establish any grading process, but it's a learning process to learn about the real situation so that we can make something that is safe but also practical, suitable, and possible to use in a real world situation. And colleagues at the University of Ljubljana have also made a video on this. They've been testing some timber, recovered timber, and they've made a video in the on-demand video section for the webinar. So if you're interested in testing of recovered wood, then I encourage you to watch that video from the colleagues in Ljubljana. It's got some videos of the testing in as well, which is great. And they talk about applying visual grading approaches, like measuring knots, and applying also machine grading approaches, different acoustic technologies, resistance drilling, that sort of thing. So they're making a bunch of measurements on this old timber to see what works and what doesn't work. And they've tested the timber, or still testing the timber, and yeah, it will be interesting to look at the data when that's finished and been processed. So what we're going to discuss actually in the webinar, well, probably you will know by now if you were in the webinar, because this will have happened by the time you watch this video, but the first question that we have is, well, what situations are realistic? We're talking about grading of recovered timber as if it was actually practically possible. At the moment it's not economic, there's no question about that you can get new wood cheap enough that no one would mess around grading recovered wood unless you had a particular need to do it. But the current economics aren't necessarily going to apply in the future. Things might change about the supply and the price of wood, and maybe legislation as well. So what situations are realistic for wanting to grade recovered wood in the near future and in the longer term? And I'm thinking in the longer term particularly about all of these massive wood CLT buildings that we're building, the huge quantities of wood in those buildings. What will happen at the end of life for those buildings? It would be probably pretty wasteful to just chip up those huge slabs. Maybe something can be done to grade, not necessarily timber sawn from those slabs, but maybe like assess the properties of the slabs and the glue lamp so that we can reuse them in another building. So yeah, what situations are realistic to wanting to grade recovered timber, and what products are we likely to put recovered timber into? Probably unlikely that we would take, for example, roof trusses and cut the timber out and then make new roof trusses, but maybe we would put that timber into CLT, because the requirements of mechanical performance and certainty of mechanical performance the requirements are much less for CLT, so that would actually be a ideal material to put the recovered wood into. And you probably would have seen a presentation from another work package on work in that area. So yeah, if we're going to come up with a system for grading recovered timber, it would be worth thinking about, well, what we're actually going to be doing with this, because maybe we don't need to replicate all of the elements of the process for new timber. Maybe we can focus on particular properties or certain situations to make our lives easier, to actually think about in the real world what they're going to be used for. So that's it. That's the end of the long version of the presentation, which has gone on for an hour or so. Yeah, I hope that's been interesting, and thanks for sticking with it, and maybe speak to you later.